Welcome to the first lesson on the DTDS, which basically stands for Discrete Time Dependent System, which is a way to model mathematically what happens to things over time. So that sounds kind of abstract, and we'll go ahead with an example, which will hopefully clear things up. So say, since you are bio students, you have a petri dish and you have some bacteria in it. Let's start with 3 bacteria. So these little dots are bacteria. Okay. And let's say it's a special type of bacteria that double every day. So every day you're going to get double the amount of it. Okay. So if I were to write initially, let's say that B, the letter B denotes the number of bacteria that you have. Okay. And we will let B0, B naught, denote the initial number. And in this case, we can clearly see that the initial number we have is 3. Okay. And so we will say that also, let's define T. So let T be the day. So that being T equals 0, that's the initial condition. T equals 1 is 1 day in. T equals 2 is 2 days in. So that's after 2 days. T equals 3 is after 3 days, and so on. And so the corresponding value of B naught would be the number of bacteria initially. B1 would be the number of bacteria at T equals 1. B2 would be the number of bacteria at T equals 2, and so on. And therefore, we will let Bn, or sorry, Bt, okay, B subscript T, be the number of bacteria at time T. And by time T, we mean after T days. So at T days, after T days, I should say, after T days. And as far as your other problems go, it'll always be time because it's a discrete time dependent system, but the T could represent seconds, it could represent hours, it could represent minutes, it could represent years, it could represent many things. In this case, and it'll be stated in the problem, but in this case, I chose it to represent the days because maybe it's this type of weird bacteria that replicates in this way. Anyway, so what we have is this kind of bacteria, okay, where we have 3 of them initially. And we know that they double every day. So these guys, they're little pests, they double every day. Mathematically, how do we say that something doubles every day? Well, we can say that B subscript T plus 1. What does that mean? This means that the number of bacteria at a day denoted by T plus 1, so that's number of bacteria tomorrow, for example, is twice the number of bacteria today. Okay, so it says B subscript T plus 1. So this is whatever T is. So T could be 20. T could be 20. It's telling us that for T equals 21, so tomorrow after the 20, we're going to have double what we had initially, or double what we had when T equals 20, right? So this is the arbitrary way, well, not the arbitrary, it's the more general way of writing it in terms of any given time, because we know that at any given time, at any given day, if we look at 1 day later, that's where the plus 1 comes from, we're going to have twice what we had at the day before. Okay, so this right over here is the equation that describes the time-dependent dynamical system that we have here. This right here, okay? And we give this thing a name. We give this thing a name. It's called the updating function. Updating function. Okay, and we call it f of x. So all we do is we replace the b of t. We just replace it by x. So the updating function over here, we call it f of x. It's just 2x. And what that gives us is that it's simply like, don't get confused by this. This is the exact same thing as that. We just use, instead of x's, or instead of b's and t's, we use x's. And all this means is that if we want to know what bt plus 1 is, we just put bt into the updating function, right? Like if I want to if I want to know what, b4 is, well, I know it's 2 times b3, right? So b4 is f of b3. Why? Because f here is the updating function, which in this case doubles the value for us, right? Because that's what the system does. So essentially, we can take this thing right over here, and if we just replace the b's this bt by an x here, that's going to give us what we would commonly refer to as the updating function. And what's important to know about the updating function, right, is that when you take a number, or not a number, when you take a value from your system. So let's say I put b3 into my updating function, I get b4 because the updating function updates it, right? If I take b0 and I put it into my updating function, right, that's going to give me b1. If I take b1 and put it into my updating function, that's going to give me b2 because the updating function updates it, right? And this also should therefore be obvious that if you apply the updating function twice to a number, so say I take f of b0, I'm going to get b2. Why? Because f of b0 over here is b1. And so this becomes f of b1, and f of b1 is b2. And similarly, if I applied the updating function 3 times to my initial value, I'd get b4. I'd get b3. I'd have to apply it 4 times to get b4. Right? Because this right over here, f of b0 is b1, f of b1 is b2, and f of b2, well, that's b3. Okay, so you can apply the updating function repeatedly to get the updated value. Okay, that's it on the updating function. So the updating function, it takes a value that your time dependent system has. So let's say the number of bacteria was 20 at one point, and you stick it into the updating function, and it's going to give you 40 if it was 20. In our particular case, right, if we write T over here and BT over here, initially we have 3 bacteria. After 1 day, we have 6. After 2 days, we have 12. After 3 days, we have 24. After 4 days, we have 48. And each of these values, right, we are simply applying the updating function, right? And because the updating function, I will recall, is f of x equals 2x. Why? Because this is basically identical to saying, well, it is the same thing as bt plus 1 is equal to b 2 times bt, right? It just, we call this x, that's it. And so we apply this to 3, we apply the updating function to 3, we get 6. We apply the updating function to 6, we get 12. So that's what it does. The updating function updates, shouldn't be anything new. So with that in mind, that puts to rest everything we had to say about the updating function. For now, let's talk about equilibrium. Okay, let's talk about equilibrium. So equilibrium basically means stability. When something is in the equilibrium, as far as you're concerned in this class, it will stay there, okay? So let's say I have a pendulum, right? And you know pendulums, right? This say it's attached over here. This is a ball. It's going to swing here. It's going to swing here. It's going to swing here. It's going to be all over the place, right? It's just going to go back and forth, assuming like no friction, no damping, whatever. It's just going to keep on going. Like it'll eventually stop after a very long time, but it's just going to swing. But if you take the pendulum and you position it just straight down, you don't move it, it's going to stay this way, right? Because this position over here is its equilibrium. So equilibrium means stability. And what stability means is no change. No change, okay? No change, something doesn't change. So let's say, let's give you, since we talked about bacteria, let's talk about another kind of population. Say we have a population of rabbits, okay? Let's use biological examples since this is a bio class. Say you had a population of rabbits, right? And the rabbits, they grow because they live, I don't know, they live on a nice big piece of land. Okay. And, there's rabbits here. I'm not going to try to draw one, but let's just say there's rabbits. Okay. And they grow and their population increases. But as their population increases, so this could be the number of rabbits over here. And this will be the time. So after, this is the number of days over here. And so what will happen is the rabbit population, if we look at it each day, will increase. But as the number of rabbits increase, let's say there's lions in the area and they start gobbling up the rabbits. And because there's so many rabbits, there's more lions. And so the lions will kind of control the rabbit population to the point where the rabbit population starts to plateau and not change. Because if it goes up anymore, then the lions will eat it up. And if it goes down lower, well, because there's so many resources available, they'll just replicate, and it'll go back higher, but it can't go up any more higher because of all the lines that lead them. So it kind of plateaus here, reaches a stable point. And this stable point is called your equilibrium. It's called your equilibrium because you are not changing. So as far as this relates to your systems, here's how. The equilibrium is when there is no change. So I'll repeat that. There is no change. So if you have your system, right, with an updating function, so say b subscript t+1, right, what's happening next, what's happening tomorrow, or the next second, or the next minute, is whatever you put into the updating function, right? So if you want to know what happens, if today is time t, day number t, and you stick the bt into the updating function, it's going to tell you what's going to happen tomorrow, right? What's going to be there tomorrow. If we say that we are at equilibrium, okay? If we're at equilibrium, that means that we don't change. So in other words, equilibrium is when b of t is equal to f of b of t. In other words, you put b of t into your updating function and you get back that same number. And so this equilibrium, right, we'll just replace it by x star. So x star is the equilibrium. The equilibrium is such that if you're at the equilibrium and you check what happens tomorrow, or the next minute, or whatever the discrete variable is, if you check what happens tomorrow or the next day or the next minute or the next year, it's going to be there. It's going to stay there. That's what the equilibrium means. Okay. And we denote that with x star. So x star right here, that's the equilibrium. So how do you find the equilibrium? Well, let's say I give you a discrete, let's do an example. All right. Now, as far as what kind of system this could represent, it could be another population of bacteria, right? So they double every day. So tomorrow you'd have 4, but you take away 15 every time, right? And then that's why the initial number is high, because it doesn't make sense to have negative bacteria, which is what would happen if you start with, say, 2. Right. So the initial values ought to make sense, but that's besides the point. So let's just say we have a time-dependent system that it's like this. This is the updating function. That's the system. Okay. And we want to find its equilibrium. So our task is to find the equilibrium. Well, what's the equilibrium? The equilibrium means that the same thing that is today is going to be tomorrow. That's what defines the equilibrium. So we put that x star into the equation, right? And what do we get? Well, the condition for the equilibrium is this. It's x star is equal to f of x star, right? That's what the equilibrium is by definition. Because the updating function is going to update, right? It's going to update what's in here. It's going to tell us whatever you put in here, it's going to tell us what's next. Well, if it's the equilibrium that you put in there, what's after the equilibrium? What's next? Well, it's the equilibrium. That's why it is the equilibrium. So this is the condition. And so we just take that and we put that into our actual equation, right? So we'd have x is equal to 2x minus 15. X star, sorry, right? So when we want to find our equilibrium, all we do is we take our updating function, f of x, and we set that equal to x, because whenever you make an equation of this kind, like you set an equation equal to something, you're asking yourself, when is f of x equal to x? In other words, when is the updating function going to give us what we fed into the updating function, which is the condition necessary for equilibrium. And then it's easy. All you do is you solve for x. So, well, if we wanted to solve for x, we can put this x to this side, the 15 on the other side, and then we get 2x star minus 1x star is equal to 15. And it's pretty simple. X star is equal to 15. So what does that mean? What does that mean about our equilibrium? Well, it means when the population reaches a number of 15, okay, it will always stay there. Okay, it will always stay there. It will not change from there because that's the equilibrium. Let's see how this plays out. Okay, so if we take 15, right? Say instead of it being b naught equals 40, let's say b naught equals 15. Okay, b naught is equal to 15. And if we put 15 into our equation, right? B naught equals 15, and we take f of b naught, we see what our updating function is. It's going to be b1, but it's going to be 2 times 15, okay, which is 30, minus 15, and it's 15 again. In other words, we got the same thing tomorrow as we had today. That's what our equilibrium is. Now, before we move on from equilibrium, we got to talk about two types. There's stable and unstable. So this is actually, this equation right over here, we'll see why later, but it actually describes this kind of equilibrium that we have over here is actually unstable. And it's unstable for a reason. We'll see why. We'll be able to show why. But just know that it's unstable. Now, what does it mean to have an unstable equilibrium? Well, maybe you were bored in class and you ever tried to take a pen and balance it on your desk, and you tried to do it. And if you got it exactly right, like it was perfect, it would actually stay there balanced and it wouldn't fall. This is actually an unstable equilibrium. It's an equilibrium because if you put it into that position, it's very hard, but if you manage to put it in that position, it'll stay there. So that's why it's an unstable equilibrium. That's why it's an equilibrium. But why is it unstable? Because any slight deviation from this, even if you tilt it ever so slightly, it's going to move away from the equilibrium position, right? Like if I tilt this pen just this way, okay, what's gonna happen is it's gonna fall down. So that's why it's unstable. Unstable is defined as if you're at that position, right? Like if you're already in this, perfectly straight up position, you're gonna stay there. That's why it's an equilibrium. But if you are removed very slightly from it, even one iota, tiny, minute difference, you just moved away from it ever so slightly, and you're let go, you're going to move away from that equilibrium. You're going to run away from it. You're going to escape it. You're going to fall down. That's why it's unstable. So what's a stable equilibrium? Well, if I take this pen, right, and I let it fall down, it's going to fall down. It's going to be at rest over here. Okay, so this is my pen. This guy, it fell down. And this, of course, is the stable equilibrium. Why? Because it's just going to stay there, right? Like if you take your pen, right, and I let it, I'm going to take mine. Boom, it fell down. It's going to stay in that position as it fell down. It's not going to move. It's not going to spontaneously move itself up into this unstable position that we have over here. So that's the difference between stable and unstable equilibrium. Stable equilibrium, you actually get to it, you approach it. Unstable equilibrium, you run away from it. So let's look at some examples of what a stable equilibrium is. So a stable equilibrium, let's just write a discrete time dependent system for it. So this would be our updating function for a stable equilibrium. So it would be b of t plus 1 is equal to 1/2 b of t plus 5, right? These two are the same thing. This is just written with the x's instead because the updating function. Anyway. Okay, so now what we have, how do we find the equilibrium? Well, we just take x and we replace f of x with it, right? Because we put the equilibrium x star into f of x. What do we expect to get out? Well, we expect to get out x star, right? Because it's the equilibrium. So we get 1/2 x star plus 5 is equal to x star. How do we solve that? Move the half to the other side and you get x star over 2 is equal to 5. So x star is equal to 10. Okay, so that's the equilibrium. So it means when we have 10, whatever, let's say this was bacteria again, they half each time, so they're dying off, but somehow I add 5 every time. When we are at 10 bacteria, it's just going to stay that way. So to illustrate a point, let's say we initially had 20 bacteria. Okay, initially we had 20 bacteria. Okay, so that was our initial number of bacteria. And let's say T denotes 1 day. So when T is 0, we have 20 bacteria. And what happens when we increment by T? Well, we put 20 into our updating function, right? We take f of 20. F of 20, right? Because it's going to give us, if we put B naught into our updating function, that's going to give us B1, okay? So we put 20 into here. Well, we get half of 20 plus 5. So what's half of 20 plus 5? It's 15. That should not be controversial. Okay, so now we increment time again, 2. And we will get, okay, well, we half 15. And okay, you might say, well, that's going to give us 7.5. What are, halves bacteria? Let's just assume that instead of it being 1 bacteria, it means a million, right? So like 20 would mean 20 million, 15 would mean 15 million. So we don't have to worry about decimals. We don't need to. So we have that, we get 7.5, right? So sorry, we do f of 15, right? It's going to be 15 over 2, that's 7.5 plus 5. So plus 5 is going to give us 12.5. Okay, so we're going to get 12.5 here. And the next one, the next iteration, I'm actually going to do it on a calculator. So this is the calculator. This is my initial value, 20, and this is the updating function. So if I take, just for practice, if I take f of b naught, I get b1, right? This is b1, that's 15, as expected, nothing new here. If I take f of b1, I'm going to get 12.5. If I take, and that's going to give me b2. And if I take f of b2, it's going to give me 11.25. Okay, and then if I take f of, right, so that's b3. And if I take f of b3, it's going to give me 10.625. And if I take f of b4, it's going to give me b5. It's going to give me 10.3 approximately. And if I were to do this an infinite number of times for a very long time, all the way, many, many times, I would eventually get 10. Okay, so it actually converges to 10. It converges slowly, but it does converge. All right, so that's an example of a stable equilibrium. As we proceed, as the system proceeds, as time goes on, we approach the equilibrium. So what do we mean by an unstable equilibrium? Well, as time goes on, we move away from the equilibrium. So this example up here is a perfect one where we move away from the equilibrium. So let's do this one again. Let's do this one again. We established already that the equilibrium here was 30, right? So this is example 2. Unstable equilibrium. Okay, and let's say our initial value, B naught, is going to be 40 again. And by the way, as far as the equilibrium is concerned, it does not matter what your initial value is. Okay, it does not matter. You will get the same equilibrium regardless of what your initial condition is. The initial condition matters to your system and how it moves, but when you're calculating the equilibrium, the initial condition doesn't have anything to do with it. So anyway, say our initial condition is 40. So as t goes on, 0, 1, 2, 3, remember the equilibrium here, x star, is 15. Okay, right? Because remember, if we plugged in 15 into our discrete system right over here, and this guy, if we plugged in 15, we got back 15. Okay, so we know that's the equilibrium, but let's see what happens when we let our system do its thing. So initially, we get 40. Well, we multiplied by 2 and we subtract 15. So 40 times 2 minus 15, 40 times 2 is 80, minus 15, 80 will be 65. And then the rest, I am lazy, I will do it on a calculator. So if our initial value here is 40 and our updating system is 2x minus 15, we initially get 65, then 115, And then if we were to get the next value, we'd get 215. And then if we were to get the next value, so it would be f of that, we get 415 and then 815. So we can see that we keep going larger and we don't seem to be getting anywhere close to 15 because we are running away from the equilibrium. It's unstable, right? So remember, if you even if we were to start, if I were to run these same numbers, but I were to start at 15, okay, you see that we have 15, like all these values, B1, B2, this is B3, they're all 15. But if I even move ever so slightly, I put a 0.1 over here, boom, 15.2, 15.4, 16, 18, we're moving away from it. So if we start at 15, that's a stable equilibrium for you. We're going to stay there. We're going to stay there. That's our equilibrium. But if I move out away from it, even ever so slightly, we're going to move away from it. Like it's just going to keep getting bigger and we're not going to go back to 15 ever. Okay. So that's the notion of stable and unstable equilibrium. Hopefully that makes sense. Now, hopefully you have seen also a problem with this approach. So what do I mean by problem is, well, when I was calculating these values of B1, B2, B3, B4, I am basically I'm iterating and repeating, applying the updating function, right? So I'm taking my B naught and I'm doing f of B naught, ooh, that's B1, right? And then I'm doing f of that to get B2. And I'm putting that into the updating function again to get B3. And then I'm putting that into the updating function again to get B4. And then I'm putting that again to the updating function to get B5. And this gets really long. Like if I ask you, what is B200? What, are you going to put this? You're going to do this 200 times? No way. Well, I mean, if you're insane, you'd want to do it, but otherwise, there is a different way. And the different way is as follows. If you have an updating function, so this is only for a particular case of updating function of the form, okay, Rx plus D. So your updating function is a straight line, okay? If your updating function is of this form, so this basically corresponds to a system that looks like this. Tomorrow, you're going to have some number R times what you have today, plus some arbitrary constant. By the way, this D right here, it could be 0, it could be negative, it could be whatever. It doesn't have to be here. It's just there to make it more complete. But this is the particular updating function. R and D are constants, okay? For that particular updating function, you can actually find an explicit solution as a function of time. And what that solution is, okay, this is the general solution. It's going to be B of t, okay, not t plus 1, B of t is going to be r raised to the exponent t times x minus, times x naught minus x star plus x star plus your equilibrium point. Okay, so this is going to be the general solution. Now, what I mean by that is you should see how useful this is, right? Because before, if I asked you what's B subscript 200, right? What's the number of bacteria at time 200? You're going to have to do this garbage 200 times. And you probably, hopefully, wouldn't be too happy doing that. If you were happy doing it, I don't know what to tell you. But instead, if you use this, all you have to do is put B200 into here, right? 200 into here. Whatever your initial number of bacteria is, your equilibrium, and you have got yourself a solution. So just to make sure that what we're doing actually makes sense, let's go ahead and take this equation, okay, and actually apply it to our system here. So our system, the one with the stable equilibrium, was f of x equals to x over 2 plus 5. Our equilibrium point was 10. We already found it, right? When we put 10 into here, we get back 10. 10 over 2 plus 5, that's 10. So that's our equilibrium. And we see it's stable because we get closer and closer to it as we go on. Okay, so this is our updating function. That's our system. Those are the values. Let's go ahead and see if we get these same values. Instead of applying the updating function repeatedly, if we go ahead and use this equation, B of t is equal r to the t, x naught minus x star plus x star. Okay, what is r? Well, if I rewrite this, right? If you just compare these two, sorry, not these two, okay, you will see fairly easily that R is 1/2, right? Because I could just write this as 1/2 x plus 5. This is our D. This is our R. Okay, and notice that the D doesn't actually pop up in here. Well, it does, but it's in the form of the equilibrium right over here. Okay, and as far as the general equilibrium, so if we have a system, a discrete system of the form, well, with the updating function, f of x is equal to rx plus d, the equilibrium, the general equilibrium for this is as follows, calculated pretty easily. We move the x over to the other side, and then we get x star 1 minus r is equal to d. So the equilibrium is just d over 1 minus r. Okay. And that should make sense if we wanted to, if we wanted to apply to like this equation to our current system, right? Our current system has updating function f of x is 1/2, so that's our r, x plus 5, that's our d. Okay, so our equilibrium x star is 5 over 1 minus 1/2, so that's over 1/2. 5 over 1/2 is just 10. So it all works out. This is just the more general abstract way of writing it. But the point is that instead of repeatedly, like if I asked you for what B200 was, and it'll probably be really close to 10. It'll probably be 10 at this point with the rounding. But if I asked you for that value, you wouldn't want to update this, you use the updating function 200 times. Instead, you just use this equation. So let's just go ahead and verify it, that it works. So say I wanted to calculate at t equals 4, right? So this is what I should get for t equals 4. I'm going to get 1/2 to the t. So that's 4, 1/2 to the 4, times x naught minus x star. X naught was 20, x star was 10, so that's 10 plus x star, that's 10. And if I go ahead and I calculate that, because I'm lazy, b of 4, I'm going to get 10.625. And if I were to calculate b of 5, I get 10.312, right? This is, by the way, the same thing as here. Hopefully you can see that. Identical. Anyway, that is hopefully good enough confirmation for you that this equation works. So let's just recap. Okay. A DTDS is basically a system that evolves through time, and it tells you how a certain quantity changes as time goes on. There's this thing called the updating function, f of x, where what you put in here, what you put in as x, gives you the next thing. Okay, so if I put in the updating function b at a given time t, I'm going to get b at a given time t plus 1. It's going to give me the next thing that comes in line. So if I give you, what happens, how many, whatever population of rabbits, if I give you the population of rabbits at, the 20th of September, on the 20th of September, if I put that into the updating function, it'll give me the population of rabbits on the 21st. And if I take the population of rabbits on the 21st of September, B21, and I put it into the updating function here, I'm going to get out of that B22, the population of rabbits on the 22nd, and so on. That's what the updating function does. So now, once we have that out of the way, we've got this idea of equilibrium. Equilibrium is when there's no change, is when we're stable, when things are staying the same. In other words, when I take a value that is the equilibrium and I put it into my updating function, I don't change from it. I get exactly that same value out. So equilibrium would be, I have a population today and it's going to be that same population tomorrow and the day after. It's an equilibrium. That's why the way you find equilibrium is by setting your updating function f of x equals to x. That's how you find equilibrium. How to find the equilibrium. Okay, you take your updating function, you set it equal to x, because mathematically the solution to that is the value of x, what it needs to be in order to satisfy this equation, right? All it means is that if you take x and you put it into f of x, the updating function, you get x back, which is exactly what the equilibrium means. So that's why solving this equation gives you the equilibrium. This is how you get the equilibrium, of which there can be two, stable and unstable. A stable equilibrium, you go towards it, okay? Think of, jumping up and you fall down. You are going towards the floor. When you reach the floor, you're in equilibrium because you're not moving, right? You take the pencil, I lift it slightly off the desk like this. I let it go, it's going to fall. Here it's in equilibrium. It's stable. It moves towards a stable equilibrium. Unstable equilibrium, well, I take a pencil, I balance it just right. It'll stay there, but the slightest nudge away from this equilibrium and my pencil is all the way on the ground. So that is enough for the equilibrium. And lastly, what we saw was the following. If we have a discrete system of the form f of x is equal to r is a positive constant, x plus d. So this actually traces out a straight line. If we look at f of x and x, this will trace out a straight line. It could be a line like this, it could be a line like that, it could be a line like this, but it's a straight line. If we look at that, okay, what we find from here is two things. The equilibrium is going to be, x star is going to be d over 1 minus r. And the other thing that we find from it is that if we want to find an arbitrary bt, it's going to be r raised to the power of t times x naught, which is your initial, or e naught, which is your initial number of whatever things you're considering, people, bacteria, lions, rabbits, minus your equilibrium, so minus your x star, and plus your x star. So there's different ways to write it. Your prof probably writes it as it's this. But the point is that this is your equation, your general solution that allows you to actually compute the value of b at any point in time. You don't have to repeatedly apply the updating function, but this only works if your discrete system is of this form.